Hi everyone, how are you? I hope you're doing well. Before I jump into the contents, I just want to share two pictures with you. The first one is our classroom. So here we go. So remember this room, the EGR 305, third floor? It's all empty. I took it last week when I visited my office, and it's quiet place now. But before we have a lecture and we have a class, I just want to share with you this classroom so that this is still a learning environment, even though in a remote instruction format. I just want you to be focused on this format. And this is my home office, my laptop computer. I use my old cell phone as a document camera, so I'm going to use it today. And then here we have for students. The reason that I put these was because I really need to have eye contact with somebody. It's kind of weird to look at the camera all the time and talk myself. So that's what I'm doing right now. All right, so what I'm gonna do today is I know we already went through most part of chapter 12, which is the transverse shear. We talked about the shear stress and the shear flow as well, but I just want to go over it again to catch up those things because we covered that topic way before the spring break, and it's almost 2 weeks, more than 2 weeks ago. So I just want to go over, start from there. Okay, so this is my document camera that I'm going to use. So what we did in chapter 12, we talked about the shear stress. The equation looks like this to find out the shear stress tau. So tau is a shear stress due to the shear force. So this V is a shear force. And then I is the moment of inertia. T is the thickness. And then Q was kind of a weird guy that we can calculate it as y prime times y bar and a prime. So we have to measure the distance from the centroid to the area that from the neutral axis to the center of the area that we are considering, and this is the area. So it is called the first moment of area. So we talked about this. We also talked about shear flow, small q, which is a VQ over I. So this is the shear force per unit length, right? So we're going to use these two equations, and I'm going to go over the first example problem using the first one, the tau equation, which is example 12.3 in your textbook. And I remember we solved this problem, but we couldn't complete the problem at the end. So let me see. I have a better resolution. The focus is not good today. I don't know why. Okay. I think this is the best so far. All right. So the problem is we have a W-shaped section. The cross section looks like this. And this beam is under a certain transverse loading. So of course we have a bending moment, but also at the same time we have a shear force. And the corresponding shear force was 80 kilonewton. The dimension for this W-shaped section is all given. The width of the flange is 300 millimeter. Thickness of the flange, which is this thickness, is 20 millimeter. And the gap between the top and the bottom flange is 200 millimeter. And this is, by the way, the doubly symmetrical section. So this is going to be the central line, which is the neutral axis, and it is symmetric about the vertical axis as well. Thickness of the web is 15 in millimeter. So those are the given information. It's quite bothering me. Let me just close it again, close it and open it again. Give me 1 second. Here we go. Here we go. Way better. All right, so way clearer, right? Okay, so the problem is we'd like to find out the tau, the shear stress at a certain location. We like to find out the shear stresses at 3 different locations. First one is here at the bottom of the top flange. So let me call that point as a B prime. So this is B prime to be consistent with the notations in the textbook. And then another point is the same point actually at the same level, but as the top of the web. Okay, so I'm gonna just mark it here. That point is B. And the other point is point C right in the middle here, point C. So we'd like to find out tau at point B, B prime, and C. And we're going to use this equation. And V, the given shear force is same as 80 kilonewton. And moment of inertia, we can easily calculate it. And that should be a constant for all these 3 calculations later. So the variables are going to be this Q and T. So I'd like to focus on the calculations for this Q and T for each case. So I'm going to make a table here. So point B, B prime, and C, and the corresponding values Q and T. I think we already went through this example in the class up to this point. So I'm just, I'd like to skip the calculation of moment of inertia. The detailed calculations are available in the solution. So the moment of inertia will be, based on the calculation, I got 155.6 times 10 to negative 6 in meter to the 4th. Okay, so I like to focus on the Q calculation, which is the first moment of area. And then T, which is the thickness. T is easier, so let's start with that. So I said the differences between B and B prime is exactly the same location, but in terms of the thickness, it will differentiate the value of the stress. So I said the point B prime is the end of the bottom of the top flange, which means the corresponding thickness is going to be this entire width of the flange. So the T for B prime is going to be 300 in millimeter, while the T, the thickness for point B, would be 15, because that is going to be, even though it is the same location, it is the top of the web, so the corresponding width is going to be 15 millimeter. And point C, of course, the thickness is going to be 15 millimeter as well. So that's the easy part. Now let's talk about Q calculation. Q, I said, is a first moment of area. So we have to find out Y bar, which is the distance from the neutral axis of the entire section to the center of the corresponding area A prime. Okay, so let's say for both B and B prime, this is going to be the area that we're going to talk about. This shaded area, we always estimate the area from the top of the section to the location where we're looking for the stress value. So this is going to be the area. So we can easily calculate A prime as 300 millimeter times the thickness of the top flange, which is 20 millimeter. Okay, so Q for both B and B prime is going to be the same, will be equal to 11 millimeter. So the area, which is 300 millimeter, sorry, times 20 in millimeters. So this is A prime part. And what about Y prime? Y prime, I said, is going to be the distance from the neutral axis of this section to the centroid, which is right here. So this distance is going to be 200 divided by 2 is going to be 100 from the bottom of the top flange to this neutral axis. And then we have to add 1/2 of the thickness of this top flange, which is 10 millimeter. So it is going to be 110 in millimeter. So 110 times, so this is going to be Y bar, and this part is going to be A prime. So that's how we can calculate the Q. And we're going to have the same Q for B prime because the B and B primes are exactly the same location, so that we can estimate the first moment of area up to that point is going to be identical. What about point C? For point C, this is the neutral axis of the entire section, and we have to estimate the area up to that point, right? So this entire T-shaped section looks something like this. So top flange and the half of the web up to point C will be area A prime. So this entire shaded area will be A prime for Q calculation at point C. Now, what about Y bar? So there are two different ways to calculate this Q for point C. One is include this combined area with the centroid of this T-shaped section so that we can just do just one multiplication, then you'll get Q. The other way is, which is easier, we're going to break it into two areas. So the top flange and this half of the web portion, and identify the location of centroid for each area so that we can have Q at C as the summation of Y bar times A prime, because we have two different areas. So what do we have? So let's talk about Y prime first. The top flange is going to be 300 times 20, and the distance from the neutral axis to the centroid of the area, it was 110, right? So 110, and then plus the area of this half of the web is going to be 100 times with 15. What is the distance from the neutral axis to the centroid of this area? It is going to be 1/2 of 100, which is 50. Okay, so this is how we can calculate the Q value for point C. The remaining steps are all available in the textbook, the solution. So you can find out the values for Q and T, substitute it into this equation to find out the tau at each location. So let me skip those steps. And let's say what if we figure out the QB, oh no, not QB, tau at B prime, and tau at C. Okay, so tau at B is V QB over I TB. And we already estimated as the QB was area of the top flange times the distance, which was 110 millimeter. And thickness at B, again, the B is the top of the web, so the corresponding thickness was 15 millimeter. So I converted everything into meters and calculate this. I got 22.6 in megapascal. Mega is 10 to 6, and Pascal is Newton per meter square. Do the same thing for tau at B prime. I got 1.13 megapascal. Tau at C, it is 25.2 in megapascal. So when we look at this W-shaped section, the I-shaped section from the side, so this is the top flange, bottom flange, and the web portion. We can draw a distribution of these stresses, okay? So the top of the section, top and the bottom, you probably remember that we have a long table for depending on the different points, and we realized that the stresses at top and the bottom will be 0 always because of this Q calculation. So it will be 0, and then the bottom of the top flange is 1.13. So here is 1.13. And by the way, the distribution of shear stresses is always nonlinear, so I'm going to use this kind of curved shape. And then here we have a jump in our shear stress because at exactly the same point, we have a difference between, in terms of the shear stresses, from 1.13 megapascal to 22.6. So there is a big jump from the bottom of the top flange to the top of the web portion, from 1.13 megapascal to 22.6 in megapascal. And then right in the middle, that is the point where we have the maximum shear stress, which is 25.2. So somewhere here. And this is also the nonlinear curve. And the remaining section is exactly the same. So let's go back to 22.6. Sorry about the poor drawing. And then going back to 1.13 suddenly, and then going back to 0. So as you can see, this is the point where we got the maximum shear stress based on this equation, BQ over IT, and the corresponding, the maximum shear stress is going to be 25.2 megapascal. So that is the end of example 12.3. So I'm going to stop here and then continue to talk about the shear flow and go over the next example problems from your textbook. All right.